Hello, this is Dr. Lori. Welcome to this video on the theory of simple linear regression. So in a previous series, we've talked about correlation and what that looks like. And so what I'd like to do is I'd like to show the relationship between correlation, Pearson correlation specifically, and simple linear regression. So I'm going to draw something here. I'm going to draw correlation over here on the left, and these are supposed to be data points. And this shows kind of a positive relationship. Remember, this is some kind of scale variable, so I'll draw my little ruler. Same thing here. And then I'm going to draw how that relates to simple linear regression. So here's what simple linear regression looks like. It has all these little dots. It has a line. It's a scale variable. And scale variable this direction. So I hope it is really super obvious that correlation and regression are very much related to each other. I'm going to talk a little bit about how they are somewhat different. They might answer sort of different questions, possibly, but mathematically, behind the scenes, they are identical. They are based on exactly the same mathematical foundation. And so with correlation, I'll just put correlation here. What we're interested in knowing is how flat is the cloud. And by the cloud, what I mean is if I were to kind of like draw a sort of a line around this, a lot of times it's sort of football shaped or hot dog shaped. Each one of these lines is a certain distance away from the line of least fit that we managed to draw. And we tried to draw a line that is collectively as close to all of those individual dots as possible. If I were, for example, to draw a line up here, it would not be as close as the one that we actually drew. So I'm going to take that one back away. So we're trying to draw a line that's as close collectively to all of those little dots. Now, if all of my dots, and let me draw these in blue, this would be an if all of my dots fall exactly on a straight line, instead of the cloud that you see in the previous one, then that would be a perfect correlation of 1. And so let me, right below here, I'm going to draw a bunch of different possibilities. So here's a correlation of basically 0. I could draw any line through this cloud and it would be just as close to all the other dots as any other line. So that would be an example of correlation equal to 0. On this other end out here, if I were to draw exactly dots on a straight line, that would be correlation of +1. And similarly, if I have a bunch of dots that are perfectly in line, but they are facing down to the right, in other words, going that direction, that would be a perfect correlation of -1. And very rarely do we have a +1 or a -1, but we can get pretty close. In between here are some other ones where the cloud is kind of sort of flattened out. So you can see a direction to the cloud, but they're still pretty far away. And maybe there's another one here where they're pretty close to the straight line. And so this gets closer and closer to 1. Maybe this is a 0.5 and this is a 0.8 or something like that. So it becomes more and more positively correlated the closer they are to being exactly on a line. So basically with correlation, what we're measuring is how flat is that cloud. Here we have a cloud that's perfectly flat. In fact, it's so flat that it's just a straight line. Now the same thing obviously could happen going this direction towards -1, where the cloud starts out as something that's just literally a round cloud, but it gets flatter and flatter until it's so flat that it's just literally a straight line. So you can see this cloud is getting flatter. The plus and the minus also give us some information about the direction of that, whether it's going down and to the right or up and to the right. But here's the important thing to remember about correlation. It does not tell us how steep the line is. And so I'm going to draw another couple of examples here. And I'm going to use the example of a clock face. All of these are going to be a correlation of 1. If this were a clock, I could go from, say, 1 o'clock down to about 7 o'clock. Let's say I have a perfect correlation of 1, and that is a correlation of +1. Also on the clock, I could go from about 8:30 to about 2:30. And as long as those are exactly on the line, that is also a correlation of +1. All 3 of these examples right here are all a correlation of 1. So correlation does not tell you how steep the line is. As long as it is going up and to the right, it tells you how close those points are to the line. How flat is that cloud? So correlation tells you how flat the cloud is. Whereas regression, and I'm going to call it simple linear regression. Simple not because it's mathematically easy. In fact, it's pretty complicated. But simple meaning like simplex, as in duplex would be 2. Like a duplex has 2 apartments in one house. Simplex is 1. It's a single predictor of our outcome variable. So simple linear regression. I've seen it in textbooks more recently called single linear regression, which I think is probably more descriptive, but I haven't seen that as much in the literature. So with simple linear regression, basically what that tells you is how steep is the line. Remember, in correlation, it does not tell you how steep is the line. The line could be steep or not steep. It's all about how flat is the cloud. With regression, we want to know how steep the line is. And so if this were a line, there's a specific place where it crosses the y-intercept, and then slope is equal to rise over run, right? And so we would have to have probably a better scale to tell us exactly what the slope is. When slope is exactly halfway, this would be a slope of 1. I'm not sure I drew that quite as steep as it needs to be. So in other words, a 45-degree angle here. That's a slope of 1. Anything flatter than that, and that's a slope less than 1. And anything steeper than that, and that's a slope that's greater than 1. In other words, the rise, you rise, that's weird, you rise more than you run. So rise over run. Slope is equal to rise over 1 from high school geometry or whatever. Now, why is this slope important? Well, the slope tells us something about the relationship between these 2 variables. And so in other words, with simple linear regression, we're asking the question, is there some kind of a linear relationship between, let's just call this height and weight. If there is a relationship, how would we describe it? And then there are 2 things that you need to know about the equation for a line in order to describe that line. First of all, you need to know where is its hinge point. From a given hinge point, you could have steep lines, you could have shallow lines. We'll get rid of those. But the other thing that we need to know is how steep is it? Right, so did I just say that backwards? Anyway, so from a given hinge point, you can have different slopes, but given the same slope, you can also have different hinge points. So this line up here, if it hinges, if the intercept happens to be here, that's a different line. Even though the slope is the same, the intercept is different. So you can have different lines because the slope is different. You can have different lines because the intercept is different. So do you remember the equation y equals mx plus b from high school geometry or algebra or whichever place they were talking about it? So those are some of the things that are a little different between correlation and regression. They are the same in terms of having two continuous variables and looking at how those two variables are related to each other. One of them wants to see how compact this cloud is. You know, a very skinny cloud is different than kind of like a bigger cloud. Regression, on the other hand, tells us something more about the nature of that relationship, the actual mathematical equation. So now that we've taken a look at comparing simple linear regression to correlation, I want to go over a couple of different things. First of all, I want to talk about what the null and alternate hypotheses would be for a simple linear regression analysis, some common types of questions that we might answer, and then also I need to warn you a little bit, or at least show you how simple linear regression is different in application from a paired t-test, because if you remember, a paired t-test also has two continuous variables, so how can we tell them apart? So let's go ahead and jump in and talk about the null and alternate hypotheses. So without getting too rid of that, so here we have there are three different ways, three primary ways that we can talk about the null and alternative hypotheses. So the first one, and I'll just say for the relationship between x and y, you would have to put in your actual variables. Slope equals 0. Now let's go back up here to our picture. What if, well, actually, let me draw it down here. That's probably better. So here's another one. What if I basically have a relationship that goes like so? See how the best line is actually a flat line. If I know something about x, does that help me know something about what the variable y will look like? It doesn't really, because no matter where I am along the x continuum, y tends to be pretty much exactly the same. The y doesn't change by x. It doesn't vary. There's not some kind of a mathematical equation. Y is the same no matter what x I have. So if I'm saying the null hypothesis is that the slope is equal to 0, that means it's just a flat cloud. This one right here in the middle, that could be slope is equal to 0 because they're just dots above and below. They're just this great big circle. So that is the null hypothesis. The equivalent alternative hypothesis is that slope is not equal to 0. I don't need to draw that on here because it'll just make more stuff try to be in one place. Another way to write the null hypothesis for regression actually has more to do with correlation, and understandably they are very inextricably that you almost can't separate them. The results that you get with regression will be the same results you get with correlation. It's just answering a different question. So we'll do the same thing for the relationship between x and y. R equals 0, or the correlation is equal to 0. In other words, I don't see a flat cloud. I see just a big globular cloud. And if I have just a big globular cloud, then I can't make an equation that describes that cloud. It's just one big giant circle right here. So in other words, if my correlation is equal to 0, I'm not going to have any kind of slope to write home about. So that's a second way. A third way, okay, so the alternative would be for the relationship between x and y, r is not equal to 0. And then a third way to write that, and you can pick and choose kind of as you're going through the homework assignment or any other place, you can write this in a way that makes sense for that particular question. The third way that is kind of more the English version, just sort of plain English, there is no, and here's the key word, linear relationship between x and y. And this goes back to this whole notion that we are talking about a linear relationship. So the null hypothesis is there's no linear relationship between x and y. Maybe there's some other kind of curved relationship. And so our linear model does not describe that curved relationship. Maybe it's even an S shape or a U shape. But our linear, this is the equation for a straight line. Our linear equation will not pick up on that relationship. So we are really testing whether there's a linear relationship between x and y. So those are the three ways that we can state the null and alternative hypotheses. And so that kind of brings me to this whole notion of what are some kind of common questions that stem from those. So I'll put that down here, common questions. So if we were out in the real world, one of the questions could be, is there, and we probably wouldn't say this if we were doing a program plan, we wouldn't say it exactly this way, but this is what we're getting at. Is there a linear relationship between the level of participation in the program and some sort of measured continuous outcome? So here's one kind. Is there I'm going to highlight linear relationship between these variables, two continuous variables? And the follow-up to that is, if we see one, if we see a linear relationship, what is it? And when we say what is it, what we're getting at is this. Is we say, okay, we think there is a linear relationship. Well, now tell me what it is. Is it a steep line? Is it a shallow line? We don't care quite so much about the y-intercept, although it is part of defining the line. We're usually mostly interested in, when I change x, how much of an impact does that have on my outcome variable? Because this is a constant. My y-intercept just stays put. When I change height, how much does weight change for a given amount of height? When I change exercise, how much does BMI change for a certain amount of exercise? If I change exercise a little, does BMI change a little? And if I change exercise a lot, does BMI change a lot? So if there is a linear relationship, then what is it? The second kind of question follows up on that, and it says, for a given x, predict or calculate what is my y for that particular variable. So when I'm initially running simple linear regression, I'm coming up with an equation. And so let me show you kind of how this goes in terms of, let's just use a very concrete example, height and weight. Because people know that people who are taller tend to weigh more, people who are shorter tend to weigh less. Obviously there's a cloud. Not everybody who is 5'6" weighs exactly the amount. There's some variability within each of those heights. But so let's write this just as if we were talking to Aunt Sue. Is height a good predictor of weight? Now, I like to take this equation and kind of break it down and turn it into, I like to take this sentence and turn it into the equation so that you can see how really math is just shorthand for saying something in a sentence. So here we have, is height a good predictor of weight? What that means is that weight is some function of height. If I know something about somebody's height, then I can tell you something about better predicting how much they weigh. So weight becomes some function of height. So let me draw that down here. Weight equals, let me get another color, some function of height. Oops, I do mean orange, sorry. Height. So notice how I squeezed in here a tricky mathematical symbol. Weight is some function of height. So then let's further refine this. Weight equals, and then this some function of, remember, for a straight line means I need to know my starting point, my y-intercept. So I'm going to call it y-intercept plus slope times height. Boy, that's really jumpy. You can read that. Okay, so here I have what that function is what's the relationship, right? What is it? So now I have weight equals the y-intercept. Going back up here, that, you know, this is the hingy point right there. What is the y-intercept? And then the slope right here is how steep is it? So where does it start and how steep is it? So that tells me everything I need to know about that. Now here's the really weird part. And this is how statistics is kind of this branch of mathematics that's different than what we're used to doing in algebra or geometry. And so let me draw this. In a regular algebra class, we would say, okay, here's the y-intercept, we give you some number. Here's the slope. Here's the height. Now calculate for me the weight. And we'll see how statistics kind of gets into this when we talk about this predicting part. Well, if I know each of these numbers, then it's just algebra. I take the slope times the height, and then I add to that the y-intercept, and I end up with my predicted weight for that particular height. And I can keep changing my height variable. I can say, well, what if I put in 160 centimeters, or what if I put in 2 meters? What if I put in all these different numbers? As long as I know what the slope and the intercept are, I can calculate all of the different weights along many different heights. Statistics is different. We have no idea what the y-intercept is or the slope. What we start with is a collection, and I'll just put little dashes. This is like 10 or 12 people, maybe 15. I collect their height. For the same people, I collect their height and their weight for all of these same people. I draw this magic cloud. And I come up with the best y-intercept and slope to match my data set, to match my cloud. So I start in a way with the answer, and I come up with the equation. That's what we're doing in statistics. So I find my y-intercept, I find my slope. Now, so far what we've been talking about is there a linear relationship between these two continuous variables, and if so, what is it? We can then take that and use it in public health for a variety of different kinds of questions. Maybe we know, depending on the weather, how contaminated swimming pools are going to be, the bacterial count. Maybe we know all kinds of things. Then we can say, wow, we're going to have a heat wave, or we're going to have some kind of an outbreak. Can I predict some other thing that I'm interested in knowing? So now that I've created this model, I can use a variety of different independent values of my independent variable and predict what's going to happen with y. And so now all of a sudden what I'm doing is I'm saying, well, I found my intercept, I found my slope. I want to, for each different level of my independent variable, I want to predict what my y variable. That looks a whole lot more like the algebra that we are all used to from high school. So these are two distinct types of questions that we want to be able to ask. Usually in the published literature, we're talking about, is there a linear relationship and what is it? In public health, though, in our application, often we want to take that predictive equation and use it to predict what's going to happen for any kind of relationship in the future. So those are my two common questions, kind of a little bit of the theory behind it, beginning with a nice English sentence that we all can appreciate and turning that into a math equation. So the last thing that I would like to do on this video is I would like to show you how a paired t-test is different from simple linear regression. Now you probably remember me saying that really all of our t-tests, so one sample, the independent, the paired, even one-way ANOVA, they are all mathematically linear regression. Linear regression is the granddaddy of them all, and they are all just the same test dressed up in a different name. And so we've named them all these unusual things because they have different applications and they have different pitfalls to avoid. So when I'm thinking about a paired samples t-test, one of the things that I can do is I can draw what's called a scatter plot or a joint distribution graph. I might have my before, whatever this continuous variable, and I might have my after, is after dependent on before. And so then, I can plot this. And mathematically behind the scenes, that this is kind of what we're doing. It's a little bit more complicated than that. But when I draw my simple linear regression, it does not look a whole lot different, right? I can draw my same scatter plot or joint distribution graph, put my little points on there, and voila. I have a continuous variable, maybe height, by a continuous variable, maybe weight. So the before here is continuous and the after is continuous. Here we have continuous and here we have continuous. The main thing over here on the paired t-test is that I am testing the same variable. And so if you ever see something where you're evaluating height by a different variable, exercise level by BMI, certain nutrition intake versus serum cholesterol levels, those are different variables. And so I cannot do a before and after. I cannot do a paired t-test on two variables that are different from each other. If I have different variables, I am stuck with simple linear regression. If they are the same or they're somehow matched or paired, then I can do a paired t-test. And the magical thing that happens with a paired t-test is all of a sudden the sample size that I need to get the same power actually goes down quite a bit because I have this pairing. I'm relating somebody to their own self. And so this is a special application of this linear regression equation where I get more power for the same sample size. And so paired means that there has to be some kind of a pairing in the before and the after. So we have to be testing the same variable in order to do that. We can't do cholesterol before, cholesterol intake before and blood pressure after. There might be some great relationship there, but we're stuck with simple linear regression to test that. So just make sure you don't get stuck. They're both continuous variables, but there are some important differences there. So thank you for joining me on this overview of simple linear regression theory.